to talk about it. So you clearly, from personal experience, know that there's like hot and cold. And people don't always understand what hot and cold are, but they did know that some things were hotter than other things, and some things were less hot, some things were colder than others, or some things were less cold. You know when it's a hot day, you know when it's a cold day. You know that in the refrigerator it's cold, and in the freezer it's colder. And then the oven is hot. And so you want to have some way of measuring that. And so that means you need to have some kind of scale. So we define temperature as a measure of how hot and cold something is. And so what is this? Well, it's degrees of hot and cold. So we have to have degrees of measure. A degree is really not so much a unit as it is, how we're measuring. Now, I already introduced one of the macroscopic effects of temperature, degrees of hot and cold, back when we were talking about oscillatory motion. So we have a harmonic oscillator, we add energy to it and it oscillates bigger. So if you have an object here and you add energy to it, then it's going to expand. And so the amount of expansion, okay, so the change in length is proportionate to the length, proportionate to a property, this coefficient of expansion that depends on the spring constant, depends on the mass of the molecules, depends on the size of the molecules, all these other sort of things that's involved in there, and it's tied up with the change of this temperature. Okay, so we know that if you add energy, that the temperature is somehow related to the energy. It's not equal to it, but it's related to it. A higher temperature has more energy in the molecules, a lower temperature has less energy. And so this relationship allowed us to start measuring temperature, because what Fahrenheit did was he realized that you got a fluid, and so that's the expansion in one direction. Okay, if you want to have volume expansion, then the change in volume is proportionate to the volume times another coefficient to change the temperature. That coefficient is, for most substances, roughly 3 times alpha. So what he did was he had a container that had a fluid in it. And so what happens is that fluid expands with temperature, it contracts with temperature. So if it gets hotter or cooler. And so we can measure how much expanding and contraction it had. And so so you put this in a narrow tube. So if it expands a little bit, it goes up the tube quite a bit. So you make a volume here that's bigger than this volume right here. And so when you have it at a certain temperature, it's here, and then when it's hotter, it's up here. And so what he defines a couple of endpoints. One is he had the idea that a horse's body temperature is more stable than a human's body temperature. So he defines a horse's body temperature to be 100 degrees. And a certain brine solution, salt water solution, freezes at 0 degrees, and that defines his top and bottom. Obviously, pure water freezes about 32 degrees, pure water boils about 212 degrees. And so this is the Fahrenheit scale right here. Okay, now the problem was these are pretty arbitrary, things he picked right here. There are other sort of things you can do this. For example, we talked about buoyancy. And so buoyancy relates to the density of the fluid times the buoyancy relates to the density of the fluid times the volume of the fluid times G. Okay, and so what happens is that if you have, this is the volume of displaced sort of thing here. So if you have an object right here, or several objects here that have defined volumes, Okay, but so they have they have the same volume maybe, and with temperature they don't change much. Remember, the expansion is different for different substances. Now, water expands and contracts one way. These things might expand and contract differently, and so what would happen is that the density of water would change if it expands. It doesn't change mass, but it will change volume. And so that would mean that the buoyancy would change. And so if these things are all weighted differently, then the buoyancy would change. And so different ones would float or sink depending on the temperature. Galileo Galilei invented a temperature system using this method. We're more familiar with Celsius degrees. Okay, so Celsius did the same thing that Fahrenheit did, except that he defines the 0 degrees Celsius to be the freezing point of water and 100 degrees Celsius to be the boiling point of water. Now, I have to point out that's not exactly correct, because this assumes that there are certain conditions. First of all, pure water. If the water's not pure, these numbers change. Secondly, it assumes a particular pressure. For example, under lower pressure, those numbers will change. Under higher pressure, those numbers will change. So typically under lower pressure, the boiling point drops. Under higher pressure, the boiling point increases. Interestingly enough, under higher pressure, the freezing point drops. So these numbers actually change ever so slightly depending on pressure and depending on purity of the water. 0 degrees is basically where you arbitrarily set the 0. Now we know that temperature is related to the energy, but clearly 0 degrees Celsius and 0 degrees Fahrenheit, neither of those are truly zero energy. So if we wanted another temperature system, okay, then one way, in fact, what we can do here is, obviously, if you want to, we need to convert. So between Fahrenheit and Celsius, you take the Celsius temperature and you multiply by 9/5 and add 32. If you want to find the Celsius temperature, then what you do is you take 5/9 of the Fahrenheit temperature minus 32. And so those are two easy relations that help you convert between the two. But as I was going to say, the 0 temperature, we want to be actually 0 energy. And so we would call that absolute 0. Well, it turns out absolute 0 is about minus 273.15 degrees Celsius. And so what we do is we can actually define a temperature scale in which 0 of that scale is the absolute 0. And we call that the Kelvin scale. And so 0 Kelvin is minus 273.15 degrees Celsius. So that means that 273.15 Kelvin is 0 degrees Celsius. That's the freezing point of water. 373.15 Kelvin is 100 degrees Celsius. That's the boiling point of water. And so these are different ways of measuring temperature. There's another scale called the Rankine scale. And the Rankine scale has absolute 0 also on it. Okay, and the Rankine scale, 0 Rankine is minus 460 degrees Fahrenheit. Now, the big difference between the Rankine scale and the Kelvin scale is that for the Kelvin scale, they both have 0 at the absolute 0. The Kelvin scale, a difference of 1 Kelvin is the same as difference of 1 degree Celsius. A difference of 1 Rankine is the same as a difference of 1 degree Fahrenheit. And so that's the big difference, is just how big the degrees are. In either case, degree is simply how far you've changed on your arbitrary scale that you picked.